All right, hello, and welcome to our Thursday evening lecture. On Tuesday, we finished talking about so a couple, a couple announcements. First, um, on Tuesday, we finished Ionic Nomenclature. This is the exam one cutoff. All right, exam one will cover everything up into and including ionic nomenclature. So that is the cutoff, and the exam is this Tuesday. Any new material we cover today will not be on the exam. We're going to start by just doing a little bit of review for ionic nomenclature. The second thing, that I wanted to kind of mention is lab activity 5. And this includes ionic nomenclature, but it also includes covalent. Oops. Uh-oh. Hang on. There we go. Covalent and acid nomenclature. And these topics, covalent and acid nomenclature, I covered in a lab lecture on Tuesday. I've added this lab lecture, just so you know. I added this to the lecture channel playlist. So it's right after Tuesday's lecture in order on the channel playlist, so you can watch it there. That stuff is not on the exam, but it is on Lab Activity 5, which I may do this coming Saturday. So that's where you can find that information. I'm not going to do the same lab lecture tonight because it'd be redundant. It's already been done. But I will be available to answer any questions you may have about it. The one last announcement that I want to make before we dive into lecture proper is about oral exam 1. Actually, I want to move this down here. So I made a post in Canvas. The next 2 weeks, we will be doing oral exams in lab. All the information is there on Canvas. The one thing that there's a few things to look for. That is correct. So I will be posting the scheduled slots. Um, and problem guide soon. I'm actually just wrapping them both up. So you will know exactly the type of problems that I'll be asking every student. It'll be different for each student, but they'll be drawn from a similar pool. But then the other thing, and I forgot to put this in the post, is an extra credit opportunity. You totally don't. So this is going to be Zoom. It's going to be one-on-one, just you and I, for 13 minutes. I'm going to ask you to work some problems, and you're going to solve them. And there'll be a dialogue. I won't be able to give you feedback till you're right or wrong because it's an exam. You'll learn after. You don't have to use a webcam for this. Totally don't have to. But the idea, kind of the goal, is to provide an alternate testing format, one where we're just sitting down and having a conversation. So I'd like if you used a webcam. I'm totally not going to force anybody to. But in the spirit of it, I want to offer an incentive to do it. So you get you get an added 20% boost to your oral exam grade. If you use a webcam. I really don't offer extra credit that frequently. I really don't offer extra credit at all, but I am for this because it's it'd be nice to connect face to face, do all that stuff. So I forgot to put that in the announcement, so I wanted to let you all know that if you want to use your webcam, then you get a 20% boost to your oral exam grade. That means you could score, you could fail every problem, and you still get 20% out of 100, right? But 20% turns an 80 into 100%, right? It turns a 70 into a 90. So, it's there if you want it. Okay. Oh, yeah. Totally. Juliana, that is a great question. So she just asked in the chat, will we be able to use or have our exam sheet with us for the oral exam? You totally can. Anything that you can use or reference during a regular exam, you can totally do that during the oral exam as well. So yeah, absolutely. Yeah. So that's it. If you have more questions about the oral exam, I'm totally down to answer those, but maybe tonight in lab. So let's go ahead and roll on into lecture. And we're going to begin with just a few more examples using ionic nomenclature. All right, so, oops. Let's start talking, or not start talking, let's finish talking about ionic nomenclature. All right, let's do a few naming problems. Daisy, so if you're asking about the lecture exam, which is my guess, yeah, for the oral exam, I'm gonna give everybody a time slot. For lecture, the lecture exam opens at class 10. Yeah, totally. And it's and you'll see I'm going to be posting the problems. Um, that'll be on there, like I said in the Canvas announcement. So it's a chance to work them live, to have a dialogue. I won't be able to tell you anything, but it's an opportunity for you to be able to, you know, not just do the answers, but also like converse with me about it, if that makes sense. Um, Daisy, I don't remember exactly. All that information is on Canvas. I made a post about the exams. All the logistical questions are there. Um, if it were, you can hit me up in lab and I'll look it up for you. But for right now, we got to get to, lecture. Aaron, um, sorry, I'll answer your question. Okay. 13 minutes for the oral exam. The lecture exam I know is longer. I think it might be 45 or 50. Okay, so let's name the following compounds. Let's go ahead and start. And let's bust out our periodic table. Move this down. Let's start with OSO4. The first, so we got to look these up. And OS is osmium. And you'll notice that osmium is a transition metal. So to name it, it's not enough just to say the name of the cation. We have to give the specific charge that it has in this compound. So it's going to be osmium something and then oxide. All right? We don't know what that something is, but we have to find it. Now, the way we find it is we know that the charge on osmium plus 4 times the charge on oxide has to add to 0. Our positives and our negatives have to cancel. Now, we don't know what the charge on osmium is, but we do know that oxide has a charge of -2, right? Oxygen has 8 electrons. It wants 10 like helium, like neon. So when it becomes an ion, it's going to have 2 extra electrons, giving it a charge of -2. So if osmium -8, the charge on osmium -8 equals 0, that means that osmium has a charge of +8. So we put 8 in Roman numerals inside our parentheses. And that is the name of this compound, osmium oxide. All right, let's do one more example. Let's do, let's write the formula for ammonium sulfate. Now, you won't find ammonium or sulfate on the periodic table because they are both polyatomic ions. Ammonium has a formula of NH4 with a charge of +1. Sulfate is SO4 with a charge of -2. Now, our anionic charge is -2. Our cationic charge is +1. So we are going to need 2 molecules of ammonium to balance the charge on 1 molecule of sulfate. All right, so we need to include 2 ammonium ions in this compound. Now, whenever you have more than one polyatomic ion, you must put it in a parentheses, right? And then we put the subscript, the number of that polyatomic ion, outside the parentheses. So the chemical formula will be NH4 2 SO4. All right, that is the chemical formula. Now, I want to do a callback to something I said last lecture. When I was introducing ionic compounds, I said ionic compounds are a metal together with a nonmetal. And then I was like, that's 95% true. But I told you not to worry. I told you not to worry about the exception to that rule, to just roll with it. And that once we got to the exception to that rule, it would make sense. Well, now we've made it. Rocks, that is exactly correct. So we've made it to that place. You'll notice that there's no metal in this compound. There's only two polyatomic ions, a polyatomic cation and a polyatomic anion. But there are no metals. And the thing is, your cation is a metal 95% of the time, unless your cation is a polyatomic ion like ammonium. All right, ammonium is a cation with no metal in it. So that is the exception to the rule. And now you can see it's not this like terrible thing you got to remember, right? Or this horrible like memorization thing that's confusing. It's just like, oh yeah, a positive polyatomic ion, that's our cation. Naturally, there's not going to be a metal. All right, so it's not world ending. You've seen the exception. And now, as of this moment, you have seen everything you need to know about ionic nomenclature. All right, you can name any ionic compound. Watch the lab lecture from Tuesday, and you've also seen covalent nomenclature, which will be covalent nomenclature and acid nomenclature. That's exam 2 material. So we'll get there in a little bit. Ionic nomenclature is on exam 1. Okay, we're gonna shift gears a little bit here, and we've been talking about compounds, right? Ionic compounds, covalent compounds. We've been talking about what their names are. We've been writing their chemical formula, all sorts of stuff. But the one thing we haven't discussed is how do they form? How do these molecules come together in the first place? How do you go from elements, all these random atoms, to molecular structures, right? We haven't talked about it, but we're going to, and we're going to lead into this discussion of how molecules form with a discussion of Lewis theory, starting with Lewis dot structures. Oops. Hang on one second. I popped this down in the wrong layer. All right, good to go. All right, so Lewis dot structures. So what is a Lewis dot structure? A Lewis dot structure is, honestly, it's just another way of depicting the electrons that are around an atom. So it's similar to a, electron configuration. It's similar to an orbital diagram. It's just another way of depicting the electrons around an atom. All right, and the way that this is done is like this. So hydrogen, if you look at its electron configuration, it's 1s1, right? Now for Lewis dot structures, so for Lewis dot structures, valence electrons are represented as dots around the elemental symbol. All right, valence electrons are represented as dots around the elemental symbol. So with hydrogen, the way you draw the Lewis structure, the Lewis dot structure, is you look at how many valence electrons we have, just one, and you represent that as one dot. All right. Now, something to keep in mind about Lewis structures is when you're looking at the elemental symbol, I'm just going to write L for some element. There are 1, 2, 3, 4 sides. So 1, 2, 3, 4 sides to the elemental symbol. And you'll see as we start adding more electrons, as we start adding more dots, that I'm going to move around the elemental symbol to each side and fill them individually before I start double filling. So, for example, if I asked you to draw the Lewis dot structure for magnesium, magnesium's right here on the periodic table. It has the electron configuration. We've got neon, and then it is on the third period, and it's 2 spaces in to the S block. So again, to draw the Lewis structure, we're only looking at the valence electrons, and magnesium has 2 valence electrons. So magnesium's Lewis dot structure would look like this: 1, 2. All right, 2 dots. If we looked at carbon, carbon is, of course, right here. Our electron configuration for carbon is helium. And the starts with a helium core, and then it's 2s2, 2p2. Now carbon has, when you look at its valence electrons, it's got 4. So that means we're going to put 4 dots on it. 1, 2, 3, 4. All right. What happens when you hit an atom like nitrogen? Nitrogen's electron configuration starts with a helium abbreviation. Then nitrogen is 2s2, 2p3. So you'll notice we have 2 plus 3 or 5 valence electrons. So nitrogen is going to get 5 dots. 1, 2, 3, 4. And now we have to double up. So we have 5. Rox, that is a great question. So you actually don't have to worry about it because on the exam, the electron configuration questions are not free response. So you'll be able to like select um, the correct electron configuration. So you don't have to worry about how do I type this because you'll just need to identify which one is correct. All right. Okay. One thing I want to point out. So we're introducing Lewis theory. Yeah, totally. It'll save you time. We're introducing Lewis theory, and Lewis theory only works for the main group. All right. It is only something that can explain the bonding patterns we observe when we are looking at main group elements. I guess I should. All right, this does not apply to transition metals. It does not apply to lanthanides or actinides. All right, it's just in the main group. And one thing that you'll notice is that there are 8 columns in the main group. There's 1, 2, 3, 4, 5, 6, 7, 8. 8 columns in the main group. Check this out. Magnesium's in the second column. How many dots did it have? 2. Carbon is in the fourth column. How many dots does it have? 4. Nitrogen's in the fifth. How many dots does it have? 5. This pattern holds true for every main group element. The main group column equals the number of dots in the Lewis structure. All right, that is true every time. Blake, that is an excellent question. And the answer is not at all. So, for example, I wrote out nitrogen like this. So I wrote nitrogen like so. You could also write it like this. You could write it like this. And you could write it like this. All of these are correct. All of these are correct because, and this will become more relevant later once we start building molecules. But the reason why these are all correct, all are correct because Lewis structures show connectivity not shape. The reason why it doesn't matter is a Lewis structure is a way of depicting molecules that shows which atoms are connected to which. It shows connectivity. But information about the actual three-dimensional shape of the molecule is not contained in the Lewis structure because all Lewis structures are two-dimensional and molecules are three-dimensional. So it doesn't matter where you put the dots as long as what is important is you'll notice that you have, this is what we call a lone pair. So as long as nitrogen has one lone pair, which you'll notice each one of these nitrogen has a set of electrons that are paired together, one lone pair. and three unpaired electrons. All right, and you'll notice each one of these dot structures, the way I've drawn them, there's one lone pair, right, and then three unpaired. As long as that's the case, your structure is correct. If you have two lone pairs and one unpaired, that's wrong. But so as long as that's there, you're good to go. All right, now that we know what Lewis structures are, we can use them to describe and to explain and understand how molecules form in the first place. All right, so for example, if let's look at sodium chloride. This is an ionic compound. You could name it if I asked you. I mean, I just said what its name was, but you could, right, if you needed to. And so we've got a sodium cation. We know. We can figure this out from looking at the periodic table, and a chloride anion. And we know this from our discussion on Tuesday, but the question is how? How did it go from being a sodium element and a chlorine element to being two ions in an ionic compound? You know? My wife and I ask this all the time. How do we go from being two single people to being a married couple with kids in this ionic compound we call a family? The answer is Lewis structures, I guess. So Lewis structures will show us how this actually forms. If you look at sodium, sodium is in the first column on the periodic table, which means that sodium, the element, has one unpaired electron. All right, let's take a look at chlorine. Chlorine is all the way out here. It is in the 1, 2, 3, 4, 5, 6, 7th column on the periodic table. So that means that chlorine has 1, 2, 3, 4, 5, 6, 7 valence electrons. All right, so you've got your chlorine atom, you have your sodium atom. Now what happens when these two react? We already know what these elements want out of life, right? If you look at sodium, it has 11 electrons. It wants to be like neon, which is 10. So sodium wants to lose one of its electrons. Chlorine has 17 electrons. It wants to be like argon, who has 18. So chlorine is out to take an electron, to get an electron. And what happens when sodium meets chlorine is chlorine's like, dude, I would kill for an electron. And sodium's like, here, take it. I don't even want it anyway. And sodium gives its electron to chlorine through a chemical reaction. We'll learn in a few chapters, or maybe next chapter, that this is called a redox reaction. What happens to sodium after it's lost its electron? Well, it lost one negative charge, so now it has a charge of positive 1. What happened to chlorine? Well, chlorine had 7 electrons. It just gained an extra negative particle. I should say 7 valence electrons. It gained an extra negative particle, so now it is negatively charged. So that is how the molecule sodium chloride forms. You've got a sodium atom that wants to lose an electron. You've got a chlorine atom that wants to gain an electron, and the two work out a mutually beneficial situation. Yes. So rocks, all main group elements want to be as stable as a noble gas, and the noble gas stability comes from their electron count, and they want to get to that stability as fast as possible. If you look at chlorine, over here, I'm going to do this in black. Chlorine has 17 electrons, and it wants to be as stable as a noble gas as fast as possible. There are two noble gases closest to chlorine. Argon has 18 electrons. Neon has 10. All right. If chlorine is going to become like neon, it needs to lose 7 electrons. But if chlorine is going to become like argon, it only needs to gain 1. And gaining 1 electron is faster and easier than losing 7. All right, so the key thing is every main group element wants to be like its nearest noble gas. They want to be like some noble gas, but it's going to be able to achieve the noble gas configuration of the noble gas that's closest to it, right? So gaining 1 electron, finding 1 electron to rip off a sodium is easier than finding 7 other elements to give 1 electron away to. So it always takes the fastest path. Nope, totally not. It'll go up if it's closer, but if an element is closer to one that has less, it'll lose electrons, just like sodium. Sodium, you'll notice, sodium is only losing 1 electron away from neon. So sodium would rather lose 1 because that's the quickest route to that sweet noble gas stability than having to gain 7 to become like argon. So you go up or down. All right, let's see where we're at. Okay, let's look at another compound. Let's look at how magnesium bromide forms. All right, well, first things first. If we look at magnesium, it's right here. It is in the second column on the periodic table. So magnesium will have 2 dots around it. Now, if we look at bromine, bromine's right here. It is on the 7th column. So bromine will have 1, 2, 3, 4, 5, 6, 7 electrons around it, like chlorine because it's in the same column. Now, we know what's going to happen, right? Bromine wants to gain electrons to become like its nearest noble gas. Magnesium wants to lose electrons, right? Bromine is closest to krypton. Magnesium is closest to neon. So magnesium wants to lose, bromine wants to gain. This is a mutually beneficial situation. So magnesium is going to give an electron to bromine. What happens then? Well, just like last time, magnesium has a positive charge because it lost an electron, right? It lost a negative charge. And now bromine has picked up a negative charge because it gained oops, it gained an electron from magnesium. But something's different here. You'll notice that bromine is happy. Bromine got that one more electron. It's now the same as its nearest noble gas, krypton. It's content. But magnesium isn't. Magnesium starts with 12 electrons, but it wants to lose 2 to be like neon. But for bromine, the bromine's like, sorry, dude, I only take 1. Tough luck. I'm satisfied. You can't make me take another one. I'm full already. I'm not going to eat more. So what does magnesium do? Well, it still has an electron to give away. So it needs to find a second bromine atom. All right, a second atom of bromine, because magnesium's going, I've got one more electron away, I'm dying to get rid of this thing, and this bromine does not yet have its octet rule satisfied. So this bromine goes, yes, please, and thank you, I'll take your electron. After that second step in the reaction, here's what we have. Our second bromine now has a complete octet and a negative charge. Our magnesium has lost 2 negative charges, so now it has a charge of positive 2. And our first bromine is still just chilling. It's happy. All right, and this is how a molecule of magnesium bromide forms. All right, now you remember when I was first introducing how to name these things, and I said, oh, they always combine in the same ratio. There will always be 1 sodium with 1 chloride. There will always be 1 magnesium with 2 bromides. Now you know the reason. The reason why there will always be 2 bromides to the 1 magnesium and magnesium bromide is magnesium starts with 2 electrons it wants to give away, but bromine starts with the need for only 1 electron. So bromine will only ever take 1 electron from magnesium, which means magnesium needs to find a second bromine to give its electron away. That's why ionic compounds always form in the same ratio. You now know the reason. I think it's pretty darn cool. All right. We have used Lewis dot structures to talk about how ionic compounds form. We're now going to shift gears a little bit and start using Lewis dot structures to show how covalent bonds form. All right. So first, with ionic compounds, it's a very violent situation, right? You have one atom stealing an electron, the other one gets mugged for its electron, right? There's a lot of conflict, there's, all that stuff involved. It's not the only way bonds can form. Turns out there's a more peaceful way, and it is called covalent bonding. All right, an ionic bond forms when one element takes an electron away from the other, making 2 different charges, positive and negative. A covalent bond is a bond where 2 electrons or more are shared between two nuclei. All right. It is a bond where two electrons or more are shared between two nuclei. And to be honest, I don't know why I put two I's at the end of this thing. Probably because I'm a bad speller. Okay. So how? How? Well, actually, let's trot out our good friend, the periodic table. Where we saw ionic bonds form, or when we saw ionic bonds form, it was always between two elements where one of them was an element that wanted to lose electrons, like sodium, and the other was an electron that wanted to gain, like chlorine. We also saw this play out between magnesium and bromide, for example. One wants to lose, one wants to gain. But what happens when you have two elements that have the same wants, the same needs, or similar wants and needs for electrons? Bromines and magnesiums are different. Bromine wants to gain, magnesium wants to lose, so that works. But what if they both want to gain? What if they both want to lose? Can bonding even happen? The answer is yes. And the path is covalent. So let's take a molecule of H2, for example. All right, how does a molecule of H2 form? Well, if we look at hydrogen, hydrogen is one electron. In the molecule of H2, there are two hydrogen atoms. So that means we got two atoms with one single electron. Neither hydrogen is strong enough to steal the electron from the other because they both have the same desires. They both want to be like helium, which has two electrons. So, how do they solve this problem? They solve it by moving closer together. They move close. They move close till they're virtually stuck together like this. All right. Now, let's do a little digital hocus pocus. If you look at this, you may be going, what am I looking at? Well, these two hydrogens are sharing. They're sharing their electrons. And if you take a moment and look at just the green hydrogen, if you pretend the orange one isn't there, it looks like the green hydrogen has two electrons. Let's do the same experiment for the orange hydrogen. What if we cover up the green hydrogen and look at the orange hydrogen? We ask, okay, how many electrons does it have? Well, it looks like it has 2 electrons. Now here's the deal. Neither hydrogen has 2 electrons all to itself exclusively, because they're sharing these two. But the point is, each hydrogen atom has access to 2 electrons. And so by sharing their electrons, they're able to satisfy their octet rule. They're able to have access to the same number of electrons helium has, and that stabilizes them. They're stabilized by sharing. What they couldn't take by force, they gained access to through forming a community. All right, this is the peaceful way of solving your electron crisis. Now, this has a name when you're sharing 2 electrons. This is called a covalent bond. All right, this is that thing that we wrote up the definition for on the previous slide. And a covalent bond, some people write them like this. Nope. But it's usually more like in high school teachers. No chemist depicts covalent bonds as 2 dots. They're always depicted as a line. All right, so whenever you have a covalent bond between 2 atoms, you always depict it as a line. All right, this represents every line in a structure. Every line in a structure represents 2 electrons being shared. All right. So that is the covalent bond. Each covalent bond has 2 electrons in it, and every line depicts this. So let's look at let's draw a Lewis structure for another molecule. All right. Let's draw a Lewis dot structure for H2O. All right, now hydrogen is in the first column. So we've got a couple H's, one dot in their Lewis structure. Oxygen is in the 6th column. So we've got 1, 2, 3, 4, 5, 6. All right. Now we can form, I'm just going to redraw this over here. Actually, not quite that far. So here, we need to make some bonds, right? And we can do that by bringing in, so oxygen needs 8 electrons, right? Oxygen wants to be like neon and have 10, 8 valence electrons, 10 total. Oxygen needs to gain 2. Each hydrogen wants to gain 1. All of these atoms will be able to do so through sharing. So if one hydrogen brings its electron close to one of oxygen's unpaired electrons, this can form a covalent bond. And if the second hydrogen brings its unpaired electron close to oxygen's second unpaired, this can form the second covalent bond. Now, this is not how you draw the Lewis structure for H2O. But I'm using this to kind of illustrate so you can see how these things come together, how they fit, they kind of click like Legos. And I'm circling them to show you where the covalent bonds will go. So the Lewis structure for water will look like this. We have two covalent bonds. You'll notice that each hydrogen, because there's 2 electrons in each bond, each hydrogen atom has access to 2 electrons, which is what it wants, and oxygen has access to 8 valence electrons, which is what it wants. All right, so this is the Lewis structure for oxygen. Yep, Carolina, it wants to be the same, hydrogen wants to be the same as helium. So hydrogen has 1, but it wants to have 2, just like helium. All right. Now, this, so this is one way of using Lewis structures to kind of build out larger structures for molecules. But if I'm going to be totally frank, it's a little bit limited, especially for the types of structures that you will need to draw in this class. So I'm going to show you a different way of doing it. And that's the way I'm going to be working problems where we're asked to draw Lewis structures from here on out. You are more than welcome to use the dot structures that we've been using up to this point. That's fine. Excuse me. But the way that I'm going to show you just lends itself better for general chemistry. Doing it this way, I actually think is more advantageous within the context of like organic chemistry, but that's not where we're at right now. And so I'm gonna teach this to you the Gen Chem way. Oh, let's see, question. Ah, yes. Okay, Juliana, excellent. Observation. Julian, I'll get to your question in just 1 second. Okay, so that is an excellent observation. Let's take a look at the periodic table. So helium is a bit of a weirdo. It belongs in 2 different places. So you'll notice that helium has 2 electrons. So in a sense, it actually belongs here, right? 1, 2. It's got 2 valence electrons. So it would make sense to stack it there. But the thing is, helium, so its electron count would be a reason why it would go in the second column. The hitch, the catch, is helium does not behave like a second column element. Actually, I'm going to move this. It behaves like a noble gas. So because it's stable, like a noble gas, because its reactivity, its behavior is similar to a noble gas, it ends up getting placed in that last column, even though its electron count doesn't match up. So helium is this one weirdo where it doesn't, it's the only element on the periodic table that whose position doesn't match the number of valence electrons. But the reason why they put it over there is because reactivity-wise, it acts like a noble gas, even though electron-wise, it has two, so could have been sorted into the second column. It's kind of like how when they put the sorting hat on Harry Potter, and he's like, please, please, Gryffindor. And the sorting hat's like, I don't know, you kind of look like you could be Slytherin. He's like, but I really want to go there. And there's that tension, you know, like, what's it going to be? That's what it's like with helium. It could have gone here, it could have gone here. Ultimately, it ended up getting sorted into Gryffindor. But it could have gone over to Slytherin. Does that make sense? Okay. So let's go ahead. Okay, so we are going to talk about. Okay, awesome. You are so welcome, and that was an excellent question, excellent observation. All right, so what we're going to do right now is we're going to do an introduction to drawing Lewis structures. This is not the only method of drawing Lewis structures, but this is the one that I think makes the most sense for this class. So this is how I'm going to do it from here on out. First, I'm going to write out the rules for drawing Lewis structures, and then we're going to do this kind of point by point by point. So step number 1. So this is actually so for drawing Lewis structures. Step 1. You want to get a total electron count. Total your electrons. All right, building a molecule is like building a house. You have a budget, and the budget is the number of electrons you have to spend, and you'll see how you use them momentarily. Second, step number 2. Select a central atom. All right, and if you're like, how do I do that? Your central atom is the atom that likes to make the most bonds. step number 3. We're going to attach the other atoms to the central. Step 4, you're going to make sure the octet rule is satisfied. We're going to complete the octets of every element in the structure. And then 5 is optional. Depends upon if you're dealing with an ion or not. You're going to add charge. All right. So these are the 5 steps. Granted, just writing them out doesn't necessarily tell you what to do or how to do them. So we're going to do some examples, and that will help this process make better sense. So, for example, let's start with, let's start slow. Let's start with F2. All right. Now, step number 1 says we need to total our electrons. And when I say total, we're only dealing, I guess I should be explicit with this. When we say total your electrons, we are only talking about the valence electrons. All right, only the valence electrons. So we look at the periodic table. Maybe scoot our periodic table over so it's not clashing with anything. Fluorine, you'll notice, is in the 7th column. So that means one fluorine atom has 7 valence electrons. So if we have 2 fluorine atoms, that's 7 plus 7, or 14 electrons to spend. All right. Now, this is our budget. These are the electrons that we have to construct this molecule of F2. Now, here's the thing. It's not like a normal budget. With a normal budget, coming in under budget is a good thing, right? Like, my wife and I got married 4 years ago, and we had a budget for a wedding. And the thing is, if we came in under budget, that was good because we'd have more money on the honeymoon, right? We paid for it ourselves. So coming in under budget was a great thing. That is not the case here, all right? This is like, building a Lewis structure is like planning a wedding with someone else's money. It doesn't matter. Spend it all. And you actually want to spend it all here, all right? So much so that if you don't spend all the electrons, you'll get the structure wrong. So you can't go over your budget, but you can't go under. You have to hit that number of electrons right out of the gate. Now, for this first example, we don't have to worry about step number 2 because there is no central atom. This is a biatomic molecule. There are only 2 atoms. So there is no atom in the center. So we don't have to worry about which one do we pick. You just put them together. And now we need to attach them. Now here's the thing. We're about to make our first bond. And when you make a bond, a covalent bond between 2 atoms, let me ask you, what is a bond made of? Right? What is in this covalent bond? The answer is 2 electrons, right? There's 2 electrons in that bond. So if we're going to make this bond, we are going to need to spend 2 electrons out of our budget. So we started with 14, now we have 12. Because we spent the first 2 to make a covalent bond. So at this moment in time, we have totaled our electrons, We didn't have to worry about a central. We've attached all the atoms together. Now we need to complete our octets. Well, the octet rule says that every element wants to have the same number of atoms as its nearest noble gas. For hydrogen, it's 2. Everything else wants 8. So you have to ask yourself, how many electrons does fluorine have access to? Well, right now, as drawn, there's 1 bond, and there's 2 electrons in that bond. So right now, fluorine has access to 2 electrons. It wants 8, so we need to give it 6 more electrons. And we can do this because we have that in our budget. We're going to give this to fluorine, give these electrons to fluorine in the form of dots. To make 3 lone pairs, to give fluorine 3 lone pairs, is going to require us spending 6 electrons. So now we have 6 left over. But the octet rule is satisfied for our first fluorine. Now, let's look at our second fluorine. Our second fluorine, again, only has 1 bond, 2 electrons in that bond. So it wants 6 more. And look at that, we have 6 more in our budget. So we're going to spend our final 6 electrons to complete fluorine's octet. All right. Good to go. So that's our first example. Let's do another. Let's do well, let's do NH3. All right, calling on our periodic table. We can identify nitrogen as being in the 5th column of the main group. So nitrogen is going to bring in and add 5 electrons to our budget. Hydrogen has 1 electron because it's in the 1st column. But because we have 3 hydrogen atoms, all 3 hydrogens together are going to bring a total of 3 electrons to the mix. So this gives us a starting budget of 8 electrons. All right, so we have successfully done step 1. Now we're on step 2. We actually have to pick a central atom. The question is, what do we choose? The first thing you want to look at is so let's go ahead and select central atom. Here, the competition is between nitrogen and hydrogen. And one way you can decipher which will be your central atom is you can look at the Lewis dot structure. Here's why. Hydrogen has 1 unpaired electron. That means that hydrogen likes to make 1 bond. Nitrogen has 3 unpaired electrons. That means it likes to make 3 bonds. All right. And that's what this means. By the way, this part right here. When you're picking your central atom, pick the one that likes to make the most bonds. Hydrogen has 1 unpaired electron. It likes to make 1 bond to complete its octet. Nitrogen has 3 unpaired electrons. It likes to make 3 bonds. So because nitrogen likes to make more, we're going to put nitrogen in the center of our molecule. Step 2 is done. Next, we need to, step number 3, attach all other atoms to our central. Going to attach our 3 hydrogens. This is going to require us to make 3 bonds. And there are 2 electrons per bond, which means we're going to spend 6 electrons out of our budget, leaving us with 2. All right, now, step number 3 is in the can. We got to go to step 4. Step number 4. Now, we need to make sure that every atom has the octet rule taken care of. All right? Now, hydrogen, its nearest noble gas is helium. It needs access to 2 electrons. And you'll notice that each hydrogen has 1 bond in this molecule. So each hydrogen has access to 2 electrons. Octet rule is good for those. Nitrogen has access to 3 bonds, which means it has access to 6 electrons, but nitrogen wants 8. So we need to give it 2 more electrons, and we have 2 more in the budget. So we're going to spend our final 2 electrons to give nitrogen a full octet. And this is the Lewis structure for ammonia. We've completed the octets. You'll notice that we haven't hit step 5 yet. You only have to worry about charge in this class. You only have to worry about charge if you start with a charge. So because NH3 does not have one, our final molecule will not have one either. All right. And I think we're going to put a pin in lecture there. We're going to come back. Oh, actually not on Tuesday, because next Tuesday is our test. So Thursday, a week from today, when we resume lecture, we will do some examples where we have an ionic charge in the covalent Lewis structure. It sounds like a contradiction. You'll have to tune in to find out. All right, that's it for lecture. I'll catch you all in at 6:45 in lab.